So where does software engineering come from? This idea of processes, and it's more than just programming and all of these characteristics that make up a good software engineer. We actually have to go back pretty far to about 1968. There was a conference sponsored by NATO, the North Atlantic Treaty Organization, and part of what motivated it was what was then being called the software crisis. So at this point in time, computers were sort of a thing, but they were a thing for big business and for science. One of the most visible projects that was happening at that time was the Apollo moon landing project. And that was a project in which, sort of unexpectedly to the project leaders, the software for the flight computer actually became the pacing item. Everybody assumed that because they were building hardware that had never been built before, they were trying to launch things into space that had never been launched that far, everybody assumed the hardware was going to be the critical path through the project. But it turned out that the software was actually the critical path through the project. This is Margaret Hamilton. She was the technical lead for the Apollo flight computer software. And what she is standing next to is a stack of its source code in a language that is not much higher level than assembly language. And by the way, this is all now on GitHub, thanks to a NASA intern who scanned it a bunch of years ago. It's kind of a fun time capsule if you want to browse it. But basically, nobody has sort of figured out that the software part of the task was going to be more complicated in some ways than the hardware part of the task. That just wasn't a thing. And so this conference was convened to ask the question, what can we do about it? We didn't think software was going to be that complicated to develop. We thought once you've got the hardware built, it's just a simple matter of programming it. But we need to now have some methods where software can be built as predictably and reliably as bridges and buildings. I mean, we know how to build those. Those are complicated, and yet they don't fall down all the time. So the first sort of attempt to do this was what we'll call the plan and document set of methodologies, which were intended to mimic essentially how those large civil engineering projects were done. There would be a project manager, and before development begins, you would sort of make this very complicated, elaborate plan. The plan would have these different phases, like requirements gathering and the actual development part, and there's a testing part, and there's a QA part. And you would have very detailed documents that track what's supposed to happen in each phase, and that's how you would know if you were making progress. You would periodically check what you're doing against what the plan said you should be doing. And if there's any change to the project, then before you make that change, you have to first go change the documentation so that the documentation matches reality. And the first process that sort of took this methodology, which some of you may have heard of, is called the waterfall lifecycle. There's a first phase in which you analyze what are the requirements of the software. You write a very detailed specification of how it behaves under all possible circumstances. You come up with a high-level architecture. What are the big subsystems and how do those subsystems fit together? What responsibilities go into each subsystem? Then you actually start doing the implementation. You have to integrate those subsystems together as well as getting each subsystem to work separately. Verification. Do the things you built actually work? Do they follow what the specification said? We might think of this today as a combination of testing and having users also interact with the software and verify that it sort of behaves the way they said. And finally, now we're going to put it into operation, and different kinds of maintenance are going to be required. You're going to find bugs that you didn't catch before. You might have to add some new features. And so each one of these phases can take, up to months. You're supposed to document everything because over that long time frame, the teams might change. You might have different people working on one phase than the people who worked on the previous phase. You need to be able to plug people in at any time, and the documentation is the truth. The plan is the truth. And when you need to change the project, you change the plan. How well does that work? Well, you can read a lot of examples in the textbook that basically add up to it doesn't work that well. And it turns out it's because there are some differences between software, which is what this is for, and hardware or civil engineering projects, which is where the inspiration came from. The users exclaimed with a laugh and a taunt, "It's just what we asked for, but not what we want." Everybody more or less knows what a building should behave like, but when you're building a new piece of software that hasn't been built before, and you ask the users, how should it function? How should it behave? The best they can do is give you a sort of best guess as to what the answer is because it hasn't been done before. So unlike hardware, software can actually change. Fred Brooks, who was a Turing Award winner, we unfortunately lost him toward the end of the pandemic, but he was the leader of the IBM System 360 operating system, which at the time it was written was the most complex commercial software project ever attempted. He sort of wrote this book called The Mythical Man Month. It was lessons learned from trying to manage this long software engineering project. One of the lessons he learned was plan to throw away one implementation. You will anyhow. And what he meant to say by that was that After you've built the system, then you sort of look back and say, oh, here's how we really should have designed that component, or how we really should have broken down those subsystems. So sometimes the only way to know how is the right way to build a system is to build it and get some parts of it not quite right, and then realize that you should have done it differently. He also has this quote that says, if you try to compensate for that by adding more people to the project, that makes things worse. Because if you add n people to the project, you've added O of n programmer effort, but there's O of n squared because they all have to talk to each other and the rest of the team to learn and come up to speed with how the project works. So adding manpower to a late project makes it later. So that observation led to other software life cycles that you can read about in the book, like Spiral and the Rational Unified process, that try to have more customer interaction while the thing is being built. But at the end of the day, the big takeaway lesson from all of this was hardware is not like software. Unlike hardware, software must be able to deal with change. Nobody expects that after you build a building, the original client is going to come back and say, actually, you know what? We actually wanted this number of floors, not that number, and we want the windows to be a different color. But with software, people expect that because it's not tangible that those kinds of changes can be made. So software has to be able to deal with change, and that makes it fundamentally different from building hardware or building bridges or building buildings.